So I'll have a look at page 51 of your worksheet. All right. This one is June 2019 P42. So for the first part, they ask you to state what is meant by electric potential at the point. It is work done per unit positive charge to bring a small test charge from infinity to a point in the electric field. This one I think has been done quite a few times already. Just copy the definition from the notes. All right. Now, the one that you want to look at is B. You have two parallel metal plates, A and B, that are held a distance d apart inside a vacuum as illustrated here. Plate A is Earth, and plate B is a potential of plus V naught. Point P is in the center region between the plates at the distance x from plate B, and the potential at point P is V. So on the figure below, show the variation of x of the potential V for values of x from 0 to D. Okay, so let's have a look at how you would plot out this current graph now. So what you do know is that your distance x is actually measured from plate B. Okay, so plate B is this one, is at positive V naught. Plate A is the bottom plate, is at 0 volts. Your x is measured from plate B itself. So meaning to say this one is where you measure your x. Okay, so let me just redraw this properly. This part here is where you tend to measure your x. You tend to measure it downwards. Okay, so if you go through the full distance, that one will be D. Okay, that's what's mentioned here. So let's just consider this. Maybe I just rewrote this. This part here is 0, but because you go through the full distance, that one will be D. This part here would be D already. Okay, because the difference between those two is D, right? So the x value at the bottom plate is already D, and the x value at the top plate is 0. So if you look at the 2 points there, the 2 plates there, at x equals to 0, your potential is plus V naught. So that's this point here. But at x equals to D, your potential is 0 volts. So it's going to be like this. Okay, so you have these 2 points here. So you now want to draw the variation of electric potential with distance. You could have either drawn it as a straight line like this, or you could have maybe thought that maybe you should be drawing a curve like this, or like this. But these other 2 curves are actually the wrong graphs, namely because we already know that is a charged parallel plate. When you have charged parallel plate, the first thing that will come to mind is E is constant. And then E is actually delta V over delta X, which is equals to gradient. So from here, if E is constant, the gradient should be constant too. So you know that you should be drawing this blue colored line here. It's a straight line, because when you draw the blue straight line there, that one is already a line with constant gradient. This one gradient constant, E is constant. Okay, so this is how you draw your variation of electric potential with distance for charged parallel plate. Then you move on to the other question, part C. So let me just clear off everything here. Okay. So in C, they mentioned that you have 2 isolated solid metal spheres M and N, each of radius R, situated inside a vacuum. Their centers are a distance of D apart, as illustrated in the figure below. Each sphere has a charge of positive Q, and you have point P that lies on the line joining the centers of the 2 spheres. This is your point P here, and it is a distance of Y from the center of sphere M. So here, your Y is actually measured from the center of sphere M. Okay, so this is the direction of your measurement for Y. Okay. And then here, in the last part, they want you to draw on the graph figure below the variation with distance Y of the electric potential at point P for values from 0 to capital D. Okay. So we've done enough examples already before to know how to draw a graph of variation of electric potential versus distance. If you look at the question here, they already told you that this one is a positive charge for M and also a positive charge for N. If I wanted to plot a graph of potential versus distance, I need to know what is the equation that defines the potential at point P. So I will still need to put a positive test charge here. Based on the workings that we've done so many times before this, I need to find out what is the potential due to M. Because this one is positive, potential due to M must be positive. And then I also need to find out what's the potential due to N. Because because the sphere N is positive, the potential due to N will also be positive. Therefore, your VP is going to be just Vm plus Vn. This is the equation that defines the variation of potential with distance. So one of the things that I did mention to you last time is that when you just look at the equation that describes to you the resultant potential between the two charges, Vm equals to Vp equals to Vm plus Vn. Because this is positive, and then because this is positive, there are two things that you will usually be able to conclude from there. The first one being that it will never be zero, because a positive plus with a positive will never be zero. And also additionally, when a positive value adds with a positive value, it will also be never negative. It will never be negative too. So that now, if you want to plot a graph of electric potential versus distance, what you're supposed to get is something like this. Okay, like what's being shown on your graph here, on your answer here. Okay, you're supposed to get a graph that looks like this. Okay, now these horizontal lines here that you see are supposed to represent constant potential inside the spheres. Okay, so we've gone through this before. Whenever you're talking about inside a charged sphere, the potential must be constant. That's where you get those horizontal lines there. Okay, and also one other thing here is this. You will notice that in terms of the potential, they seem to be at the same level, and then your minimum point seems to be at exactly the midpoint here, where this one is d over 2 and this one is d over 2, right? So why is it that potentials here are the same? And why is it that the midpoint, the minimum point is right at the center here? In other words, why is the graph symmetrical here? Okay. So why do you say that the graph is symmetrical here is because of what the question mentioned earlier here. You notice that this one, they told you that each sphere has a charge of positive Q. So what you can actually conclude here is that since both spheres have same charge, since both spheres have same charge, therefore the graph is symmetrical. Okay, the graph will be symmetrical. Okay, so that's why you get that shape that you see now. All right, so this green line here that I highlighted is what you're supposed to get. Okay, so make sure that your constant potential line is only at R. It's only at R. And then after that, your other constant potential line will be at D minus R. Okay. Because here the question already told you this one is radius R, this one is also radius R. So it will be constant potential from 0 to R and from D minus R to D. Okay, and then after that you just draw your line like this going to midpoint and make sure it's right at the center. Okay, so right at the center should be somewhere around here. This one I believe is already d over 2. Okay, so that should be it for this question. So also just make sure that your potential is constant for both spheres and they're of the same value. All right. Okay, so if this is okay, then I'll move on to another question. This one is going to be page 43 now. Have a look at page 43. This one is November 18 P42. Okay. So again, they've been asking this question a lot of times already. Describe what is meant by electric potential at a point. This one, I'll probably just skip this. It's just put down per unit positive charge and bringing a small test charge from infinity to that point. Just take from it from your notes. Now, number 2, this one is quite new. They tell you to state the relationship between electric potential at a point and the electric field strength at that point. So based on what we've just learned, there is a connection between potential and field strength, isn't it? Just now, what I mentioned to you was that electric field strength is actually equals to negative potential gradient. Okay, the potential gradient itself gives you the magnitude of your field strength, and the negative gives you the direction of your field strength. It's in the direction of decreasing potential. Okay, so when you define your field strength, this negative sign is actually important to be included. Okay, because it tells you direction. Okay, but there's also another different way of writing the same thing. This one is you split it into 2 different sentences. This one is the statement in red below. If you wanted to kind of separate it to consider magnitude, to consider direction, the first one you can probably write is that field strength is equals to potential gradient. This one covers the magnitude part. The direction part would be you saying that field strength is in the direction of decreasing potential. If you have written this, you will have gotten your 2 marks too. No issues there. All right. Okay, then after that, you look at B. In B, you have 2 similar solid metal spheres A and B, each with radius r, situated in a vacuum such that the separation of the centers is d. The charge positive Q on sphere A is larger than the charge positive Q on sphere B. So you have a movable point P located on the line joining the centers of the 2 spheres. The point P is the distance x from the center of sphere A. So your x is measured from the center of sphere A. Okay. Now, after that, what you want to do is to plot a graph of variation of electric potential V between the centers of 2 spheres with x. It is kind of similar like the one that you've just done, but there is one key difference now. That one being that your potential is not going to be the same. It's not going to be at the same level. Your graph will not be symmetrical also, unlike the previous one that you've just done. That one comes due to the fact that you had this statement here. The charge positive Q on sphere A is larger than the charge positive Q on sphere B. This one already tells you that the graph will not be symmetrical. Okay, it will not be symmetrical. So based on what we learned already, what is the equation that kind of tells me what is the potential at P? Knowing that sphere A is positive and sphere B is also positive. This one, we've done so many of this thing already before. Potential due to A is going to be positive because sphere A is positive. Potential due to B is also going to be positive because sphere B itself is positive. Therefore, VP is equals to VA plus VB. So in general, your graph shape, again, should be something that looks like this now. Okay, it should be something that looks like this now. All right. So this one, based on this, I know I have a minimum point. This one is never 0. never negative. Okay, so how do I then kind of work out the exact shape? Is due to this one. If I expand the equation a little, VP is equals to VA plus VB. Without talking so much about it, let me just try and write it out first. 1 over 4 pi epsilon naught QA over RA plus 1 over 4 pi epsilon naught QB over RB. So that's why I mentioned to you, I actually did the same thing for you last time. If your X increase, your RA will increase such that your VA will drop, but your RB will drop such that your VB increase, so that now VB will be more than VA. But on the other hand, if your X is dropping, your RA would drop such that VA increase, but your RB your RB would increase such that your VB drops. So in such a case, your VA will be more than VB. Okay. So what you're supposed to kind of conclude from here is this: closer to sphere A influence, maybe I don't write influence now. Maybe I should use a better word. Effect due to A is stronger. Okay. And then closer to sphere B, effect due to B is stronger. Okay, so this is what I can kind of conclude. The more I go towards sphere A, the effect due to A will be stronger. The more I go towards sphere B, the effect due to B will be stronger. Okay, so just take that in mind. And then after that, let's just consider this. V is by right 1 over 4 pi epsilon naught Q over R, right? Such that B is actually proportional to Q. So this one, I can say that if I have a larger Q, my potential tends to be larger. If my Q is smaller, my potential tends to be smaller. So what can I say from here is this. You see, the charge on sphere A is larger than the charge on sphere B. This one would already kind of tell me this. Because QA is larger than QB, the potential due to A will be larger than the potential due to B. Okay, that's why here you see that this line is higher than this line. It's because VA more than VB. Okay, so that one covers the part why the first constant potential line is higher than the other. Next comes the part where you have your minimum point. Okay, if this one here is distance D, let me just draw it out for you. If this one here is distance D, because you're not having the same charge in the first place, one being larger than the other, it's not reasonable to assume that your the minimum point will be right at the center. It will be slightly skewed towards one side. Okay, so what we could say here is that this one should be less than D over 2. Wait, sorry, my mistake. This one is not less than D over 2. This one should be more than D over 2 actually. This one should be more than D over 2. This one should be more than, why do I keep writing 2? Sorry, just give me a moment. This one should be more than D over 2. whereas this one should be less than d over 2. Okay, so why do I need to say this? Is again due to your equation. V equals to 1 over 4 pi naught, 1 over 4 pi epsilon naught q over r. The first relation that I gave you was this. V is proportional to q. There's another relation that you can also kind of get from this. If I try to rearrange the equations, where I still assume that 1 over 4 pi epsilon naught is a constant, I can actually get this relation. Q is proportional to potential times R. If assuming that this thing here is constant, this which is known to be true. Okay, since my 1 over 4 pi epsilon naught is constant, I can say that Q is actually proportional to VR. Now, when you take potential times with R, the V times R here is actually akin to the area under your potential distance graph. Okay, so what I can then say from here is probably something like this. Okay, so let me just rewrite it here so that it's more consistent with what I just wrote. This one here is area under your graph. So that now, if your Q is large, your area is large. The area under your potential distance graph is large. Okay, this one Q is large, area is large, Q is small, area is small. Okay, so again, because QA is more than QB, you could also say that area for A should be larger than area than for B. Okay, area due to A should be larger than area due to B. So when I say the area, it's kind of like this. This one is something like your area for A. And then this part here, let me find a color. This part here should be your area due to B. Okay, so area A should be more than area B. Your minimum point should be skewed more towards the right hand side. That's why you're getting this graph that you see right over here. Okay, so let me just erase everything out and draw for you the proper line. Okay, so you first need to draw a line of constant potential for both spheres, but you need to make sure the first one is higher than the other, mainly due to the fact that charge of A is larger than charge of B. Okay, then after that, when you want to draw your minimum point, just make sure it's skewed more towards the right hand side. Okay, so this one I think I probably just should write this somewhere here. The minimum point is skewed towards the right. It's skewed towards the right. Okay. When you skew your minimum point towards the right, you're gonna get a smaller area than the one before it. Okay. You skew your minimum point to the right, the area on the right side will be smaller than the area on the left side. This one will directly give you area A being bigger than area B. Okay. So that's why the minimum point is skewed towards that side. Right? And your minimum point will never be 0 and it should never be negative based on what I've explained before. So you just draw your lines and connect them like this. You should get your answer already. Okay. So this one is worth 4 points. Just like that. Okay, so if this is okay, can you guys just look at page 1 of your worksheet? So have a look at page 1 of your worksheet. This one would be June 2015 P41. Okay, so in your current question, you have a charged metal sphere that is located in space. Measurements of the electric potential V are made for different distances x from the center of the sphere, and the variation with distance x or the potential V is as shown here. So you have a charged sphere. You are interested in the variation with distance x from the center of the sphere of the potential. So you want to find out what is the potential here, 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 and here. You want to find out a graph. Sorry, it's not that you want to find a graph. They're already given you the graph. So the situation is described here is that you have a charged metal sphere, and they drawn for you the graph of electric potential versus distance. Okay, so you should already know how they got this graph shape in the first place. Okay, so the first thing that we know is that this line here must be constant potential. Okay, when it's constant potential, we know that this is inside your sphere. Okay, so let me just redraw this. This part here is inside your sphere. Then this other side here is actually outside your sphere. Okay, so inside your sphere, you must have constant potential, and then outside your sphere, you would have B is equals to 1 over 4 pi epsilon naught Q over R, such that potential is inversely proportional to R. That was how you got this exponential decay curve in the first place. Okay, so that one is how they got this graph shape. Okay, then in part A, use your figure to determine the electric field strength in Newton per coulomb at the point where x is 4 centimeter, and then explain your working. So now they are asking you to determine the electric field strength at 4 centimeter, which is at this point here. Okay, this is the point that you're interested in. At 4 centimeter, what's the electric field strength here? But you see, you have a graph of potential versus distance, not electric field strength versus distance. So how do you relate potential with field strength? This one is through the equation that you just learned earlier, where we say field strength is negative potential gradient, right? So the magnitude of your field strength is actually the potential gradient itself. Your delta V over delta X is your gradient now. Okay, so since the question mentioned that you need to explain your working, the explain your working part is actually you mentioning this sentence here. Magnitude of electric field strength is your potential gradient. Okay, so your E is actually the gradient, specifically the gradient of your tangent drawn at 4 centimeter. So you just try and use your ruler, draw some sort of line that is tangent to the 4 centimeter mark. Okay, find the gradient of that tangent. So you find the gradient of that tangent, not forgetting your power of 10 here and changing from centimeter to meter here, you should get your answer as 4.33 times 10 power 4 Newton per coulomb. Okay, but because when you're talking about drawing a tangent and finding the value, every student tends to have a different value. The marking scheme has actually given you a range here. If your E is between 4.2 to 4.8 times 10 power 4 Newton per coulomb, it will be acceptable. Okay, so that is for this particular question. This one is not really that difficult. Okay, so that one is part A. How about for part B? If you go down a little and have a look at part B mentions this. The charge on the sphere is 8 times 10 power minus 9. So this one is 8 times 10 power minus 9 coulomb. Use the figure to state the electric potential at the surface of the sphere. How do I know what is the potential at the surface of the sphere? So if you look back at this diagram here, just like I mentioned to you, the region where you have constant potential is inside the sphere, right? So where do you suppose is the surface of your sphere? The surface of your sphere should rightly be at this point here, right? This is the surface of your sphere. So the potential at the surface of your sphere is really just 3.6 times 10 power 3 volts. Just like that. Okay? Alright, so this one is your potential at the surface of the sphere. Alright, so this is pretty straightforward. Then after that, if you move on to part 2, part 2 you cannot do because this is on capacitance. This is the chapter for next week. Alright, so just leave this one first. Okay, then we move on to another separate question now. This one should be page 3 now. Page 3 is June 2015 P42. Okay, so I will look at page 3, June 15 P42. So first part, define electric potential at a point. This one I'll just skip. Is work done in moving a unit positive charge from infinity to a point in the electric field. Now, if you look at B, two positively charged metal spheres A and B are situated in a vacuum as shown in this figure. You have a point P that is on a line joining the centers of the two spheres and is a distance x from the surface of sphere A. Okay, so this is point P and is a distance x from the center of sphere A. So the variation with x of the electric potential V due to the charge spheres is as shown below. Okay, and then after that, they ask you to explain one other thing. If you just look at part 1 of the question, they're asking you to state how the magnitude of your electric field strength at any point P can be determined from your graph in figure 5.2. Okay, so how do you determine the magnitude of your electric field strength from your graph of potential versus distance here? Okay, this is a graph of potential versus distance. So we already done this kind of question so many times. We already know that VP is actually VA plus VB, where both VA and VB are positive. Here the question didn't mention this. They never told us what is the sign of the charge. But from looking at this graph here, where it's like this, you should already know it's VA plus VB. Okay, so this one is how they got the graph shape, but the question isn't interested in that. They're just interested in finding out how do you get the magnitude of your field strength from the graph. So here you can just say it's obtained from the gradient of your graph, because E is negative potential gradient, is negative delta V over delta X, where your delta V over delta X is the gradient of your Vx graph. This one will give you your magnitude. Okay, so you just say gradient of the graph. That one will be sufficient. Okay, now then if you move on to part 2, in part 2, without any calculation, describe the force acting on a positively charged particle placed at point P for values of x from 0 to 10 centimeter. Okay, so without any calculation done, how would you describe the variation of the force with distance? With the distance stated there. So let's just consider how the graph looked like before. This is a graph of V versus X, isn't it? So just now, what the graph looked like was something like this. Okay, it looks something like this. It's a bit higher on the left side, isn't it? Like this one. Okay, So notice that this one, they didn't have the constant potential line like the ones that you've drawn before. That's because your x is not measured from the center of sphere of the spheres. You see, if you read your question carefully, your x is from the surface of sphere A. X is measured from the surface. It's not measured from the center. So since you're not measuring from the center, you don't pass through the inside of the sphere, you don't need to draw the constant potential line. You only need to draw from surface of sphere A to surface of sphere B. That's why the graph shape looks like what you see right now. Okay, so how are you gonna describe the variation of the force with distance? Okay, there are a few things that you could probably do from here. Let's just say that I try to divide the graph into two separate sections like this. That is based on my minimum point here. The first thing you probably would look at is how the gradient varies for this first part here. Now for this first part here, I know that my gradient is decreasing. So my potential gradient, okay, maybe I should not write it here. I'll write it on the left hand side. For this section, section 1, for section 1, for this point number 1 here, you can see that your gradient is actually decreasing, right? From here to here. So here, what I could say is this. My gradient is decreasing. My potential gradient is decreasing. So my E is decreasing. Okay, my gradient decreases, my potential gradient decreases, so my E decreases. Therefore, my FE decreases. Okay, this is what I can conclude. Therefore, my FE decreases. How do I know that? It's because of E equals to FE over Q, such that FE is equals to QE. If Q is a constant, FE is proportional to E. So now if E drops, FE drops. Okay, that's point number 1. Okay, how about point number 2? You look at the minimum point here, this part here. This part here is where my point number 2 here. This part here is where my gradient is 0, potential gradient is 0, shear strength is 0, therefore electric force is 0. Okay, that's what I can say for the minimum point there. And then now you look at the remaining side. This one, let me just use orange. How would you describe the variation in your gradient here? This one say is number 3. So for number 3, my gradient is actually increasing. So my potential gradient is increasing. My E is increasing. Okay. But be careful about the direction of your gradient now. This one here, you notice for the first point, the gradient is negative gradient. But for the third one, the third point, this one is positive gradient, right? So between 1 and 3, you actually have changed direction. Gradient change direction, isn't it? So here, you see that gradient change direction. Your FE also change, your E and FE change direction. Okay, simply put. Because you notice that your gradient here has changed direction, your E and FE change direction. Okay, you can see from here already, your gradient is positive and is increasing. So if you look at point 3, I can say that gradient is increasing, potential gradient is increasing, E is increasing, but in opposite direction. So what I could then say is this. Therefore, FE increases in opposite direction. Okay. So these are 3 points here. But the marking scheme actually only wrote number 2 and number 3. Okay, from what I've just described here, there are 3 points, right? But when you look at the marking scheme actually only took point number 2 and point number 3. For some odd reason, it never took point number 1. Okay, instead they wrote something else. If you look at the written answer there, the first point that they wrote was that the force is maximum at the surface of sphere A where x is 0. This is actually correct because if you just look at the point where x is 0 itself, meaning to say you look right over here, this is the point where your distance is 0, this is x, and this is potential, right? So if you just look at the gradient right over here, the gradient of the tangent right over here, this is where you have gradient maximum. Okay, maximum gradient. Okay, so gradient is maximum. You could actually say something like this now. Let's just call this point number 4. You could say that you have maximum gradient, maximum potential gradient, maximum E. Therefore, FE is maximum. Okay, this one is what they put for point number 1 in your marking scheme. And after that, you look at the subsequent statement. The force is 0 is x is equals to 6 centimeter. That is point number 2 here. The force then increases, but it's in the opposite direction. That's point number 3 here. Okay. But let's just say you just want to have a very complete answer. You can write all 4 points. No? Okay. If let's just say in the exam, you had just written the first 3 points that I wrote, it should be correct. Okay. It's just that for some odd reason, the marking scheme chose to write another different point. Okay. But for the sake of completeness, you can just write all 4. All right. Any 3 of them would be correct. Okay. So that's for this one. Then if you're okay with that, let me just move on to number C. Okay, for part C, your positively charged particle in B2 has a charge of Q and mass m given by the expression Q over m is 4.8 times 10 power 7 coulomb per Kelvin. Initially, the particle is at rest on the surface of sphere A where x is 0. It then moves freely along the line joining the centers of the spheres until it reaches the surface of sphere B. So on figure 5.2, mark with letter M the point where the charged particle has maximum speed. Okay, where is the point where you have maximum speed? Okay, so how will you do this? Right, before I go to that, let me just write certain things here on the graph that I just draw. For point number 1, this one I should probably have written it as gradient decrease. For point number 3, this one I should have written it as gradient increase but opposite direction. Okay, this one will make your graph look a lot more complete now. Okay, so how do I know where's the point where you have maximum speed? This one was already something that we discussed last week just by looking at energy changes. I already know that this minimum point here is where I have max speed. Again, this part here is where I have max speed. This one should be where my point M is. But why do I say as my point with max speed? Let me just try and draw it on the top here. This one is another explanation, but without so many writings there. The mistake I did last week was that I tried to write so many things on the single diagram to the point it got really confusing and messy. So I'm going to split it up now. So say this one is your graph of potential versus distance again. This part here being your minimum point. Okay, this part here being your minimum point. What you could actually say is this. If you go from here to here, you could clearly see that your EPE is dropping such that your KE is increasing. Again, this one is what you can see. Then after that, if you go from here to here, in this direction, you likewise can see the opposite happening. Your EP increases, but your KE is dropping. So the conclusion that you can actually get from here is that from here to here, you're actually speeding up. And then from here to here, you're actually slowing down. Okay, so at this point here, where you change from speeding up, then suddenly you slow down, this point here must therefore be the max speed. Okay, because you see, you have been speeding out all this while, and then suddenly you start to slow down. That means you already dropped from your maximum point. You already dropped for your maximum speed. The point where you start changing from speeding up to slowing down, therefore must be your maximum speed net. Okay. And this one also something I explained before. This is a graph of potential versus distance, right? It's also akin to your electric potential energy versus distance graph because of this equation from 1 or 2 lessons ago. Potential is EPE over Q, right? So that EPE at a point is equals to QB. So if Q is constant, EPE is proportional to B. Okay, that's why I can say here EPE drops and EPE increases after that, even though it's just potential. Okay, so the point M here is the minimum point. If you now look at part 2, use your figure 5.2 to determine the potential difference between the spheres. Okay, the potential difference between the spheres is actually this potential difference. Okay, they want you to find the delta V between this point and this point. Okay, so you should get an answer of 570 minus 230, giving you 340 volts, just like that. All right. And then last part here. Use your answer in part 1 to calculate the speed of the particle as it reaches the surface of sphere B, and then explain your working. Okay. So here, this one is asking you to find out the speed of particle as it reaches the surface of sphere B. If you look at page 34, if I'm not mistaken, you also had a similar graph, and then the end part of the question asks you to find out the maximum speed of the particle. Now you look at your current question, the one on page, what page already? This one is page 3, is it? The one on page 3 is actually the exact same situation, the exact same sphere, both positively charged, but this time the last part here doesn't want you to find out the maximum speed, but rather the speed on reaching the surface of sphere B. Okay, so here you again would use conservation of energy, but this time it is applied from here to here. Let me see whether I can draw that arrow here. It's applied from here to here. This pink color arrow here. You're considering from this point to this point. So you consider the pink color arrow, the energy changes. In general, it is getting lower, your EPE. Your EPE is getting lower. In return, your KE must increase. So you consider the energy changes between those 2 points. Your decrease in EPE is equals to your increase in KE. Your change in EPE is just Q delta V. Your change in KE must be half mv squared minus 0. On reaching the surface of sphere B, this one here was your sphere B, right? You should have a certain speed. Your kinetic energy is based on this speed at sphere B. But when you're talking about at the surface of sphere A, when you're talking about the surface of sphere A, right over here, recall that the question mentioned that your particle is at rest on the surface of sphere A. So here, because it is at rest, you do not have KE. KE is actually equals to 0. That's why here there's a 0 here. You only have KE upon reaching sphere B. Okay, so it's half mv squared minus 0. So after that, what you just want to do is that you need to play around with the equation. You do not have the values of your charge and mass individually, but what you have is the ratio values. So what you do is you want to shift this m to this side, so that you get q over m times your potential difference equals to half v squared. And then after that, it's just a simple matter of substituting all the values in until you get the final answer as 1.81 times 10 power 5 meter per second. Just like that. Okay, pretty straightforward. So from doing all these questions right now, I think you should be able to start to see that there are certain repetitions in the way they ask the questions. And there's also repetitions in the method. Okay. So if this is okay, then I go to one last question. We probably can do one or two more questions before we end this chapter. Okay, I will look at page 41. This one will be November 2018 P41. Okay, so November 2018 P41 should be this one. All right, so again, we have that same repeated question, define electric potential, so I'll skip this. Now, in part 2, state the relationship between electric potential and electric field strength at the point. This one is actually a repetition of one of the earlier questions. You can actually just say electric field strength equals to negative potential gradient to get your 2 marks. Or you could just separate it as saying field strength equals to potential gradient, or field strength is in the direction of decreasing potential. Whichever answer you like. Okay, either the first one or second one will do. Now for part B, you have two parallel metal plates. Let me just clear off everything here. Now for part B, you have two parallel metal plates A and B that are situated at a distance of 1.2 centimeter apart in a vacuum as shown. Plate A is earth and plate B is at potential negative 75 volts. You have a helium nucleus that is situated between the plates a distance x from plate A. Initially, the helium nucleus is at rest on plate A where x is 0. Then after that, they mentioned that the helium nucleus is free to move between the plates by considering energy changes of the helium nucleus. Explain why the speed at which it reaches plate B is independent of the separation of the plates. Okay. So let's consider now that you have a helium nucleus. You place it at rest on plate A where x is 0. So when you're talking about your helium nucleus is alpha 42 with a charge of plus 2e and a mass of 4u. Essentially, you are having a positive charge. So you place a positive charge here. It is at rest on the surface of plate A, and your x is 0 here. Okay, your x is measured from plate A itself. Okay, so this one is where you measure your x. It is from plate A itself. Okay, so from here, your alpha particle will actually start to move upwards. Okay, your alpha particle will actually start to move upwards. You can actually think of it as this now, because you see this is negative and then this is positive. There's actually attraction here. Okay, and then this one is 0 and then this is positive. There's basically nothing here because there's neither repulsion, there's neither attraction here. But the top part here, you have negative and positive. You definitely have attraction. Your charged particle is definitely going to move up. Your electric force is also going to be definitely outwards. But if again you want to kind of like see why is your electric force outwards, it's similar to what I just mentioned to you earlier, where I tell you that direction of E field I'm just going to shorten electric field as E field, okay? Direction of E field is from higher potential to lower potential. So in your case, 0 volts is considered to be higher potential. The negative 75 volts is considered to be lower potential. So direction of E field is going to be upwards here for your case. Direction of E field is going to be upwards. Okay. And then the last thing here to note is that direction of Fe on positive charge follows direction of E field or field strength if you want. Okay, so here positive charge field strength is directed upwards. Your electric force must therefore be directed upwards. That's why it moves upward. Okay, so I know it definitely will move up. Okay, so now when it moves up, what do you suppose will happen? You started from rest here. You have an electric force acting on your charge. You have a resultant force here. You're going to have an acceleration on your positive charge. It's going to accelerate from the plate A to plate B. It's going to have an increase in speed such that when it reaches B, you would have actually some speed. Okay, but the question wants you to explain why is it that the speed is actually independent of the separation of your plates. Your plate separation has nothing to do with the speed with which it will reach plate B. So this one, you consider energy changes first. If you go from here to here, I already know I speed up. So my KE increases. And if my KE increases, my EPE must therefore drop because of conservation of energy. So I could say that gain in kinetic energy is equals to loss in electric potential energy. So now my gain in kinetic energy is just half mv squared minus 0. The half mv squared is from this top part here. The 0 here is from the bottom part here because it's at rest. And then after that, your loss in electric potential is just Q delta V. Eventually, you get half mv squared Q delta V. So notice here now that your V will only depend on the mass, will only depend on the charge, will only depend on the potential difference. It has nothing to do with your plate separation. It's not inside the equation at all. So you could actually just say that V is independent of separation because the separation is not inside the equation. Just like that. Okay. So that is for part 1. And then you move on to the second part. This one is already on your calculation. So let me just clear off everything here. And redraw something here for you. Just give me a moment to clear everything off. Okay, now in part 2, as the helium nucleus moves from plate A towards plate B, its distance x from plate A increases. Calculate the speed of the nucleus after it has moved a distance of x 0.4 centimeter from plate A. Okay, so let's just consider this. Your plate A is here. Your plate B is here. Okay, so this one is A. This one is B. This one was at negative 75 volts. This one was at 0 volts. And bearing in mind that your x is actually measured from plate A. Okay, so they say to you now that you need to find the speed of your alpha particle after a distance of 0.4 centimeter. Now, the full distance between your plate A and plate B is given inside the question as 1.2 centimeter. Okay, it's already given as 1.2 centimeter. So what you're trying to find now is the speed not upon reaching plate B, but rather some point before reaching plate B. You are interested in a distance of 0.4 centimeter away, which is probably somewhere around here. Let's just say that it's this point here. at 0.4 centimeter. Okay, that you're interested in. And then this part here, the full length was 1.2 centimeter. Okay. So your alpha particle, same as before, it tried to move from here all the way to here, but this one was moving from rest. So when it move all the way to here, you will have a certain speed. Okay. Now you apply conservation of energy. From here to here, you will say KE increase, EPE drops. Same thing as the one that you did before. So if you say increase in K equals to decrease in EPE, you get half mv squared minus 0 equals to q delta v. So that half mv squared equals to q delta v. Now, if you just look at the equation now, you know what is the mass of your alpha particle. The v is what you want to find out. You also know the charge of your alpha particle, but you notice that there's one other unknown here, the potential difference. The potential difference is unknown. You need to find out the potential difference between the plate A and the 0.4 centimeter mark before you can even solve this question. So here, you are required to find out what is the delta V here. Okay, so you can actually use something like ratio here. You see, between plate A and plate B, for a distance of 1.2 centimeter, what's the potential difference between the 2 points? Is 0 minus negative 75, right? So here, I can say that over here, my potential difference is 75 volts. So what I want to do now is this. If I know that 1.2 centimeter gives me a potential difference of 75 volts, what about 0.4 centimeter then? It will actually be 0.4. This one, let me just use a different color. This one, my potential difference of 0.4 centimeter would be 0.4 divided by 1.2 times 75, giving you 25 volts. I know I can use a ratio like this because the variation of electric potential with distance is linear, okay? This is what I mentioned to you earlier in the lesson. So say right now, if I try to draw for you a graph of electric potential versus distance, say this one is V to X, it should be linear like this. Okay, it's going downwards because I know that at 0, at the X equals to 0 mark, my potential is 0, but at the X equals to D or 1.2 centimeter mark, my potential is negative 75 volts. I'm interested at a point somewhere in between here where you have 0.4 centimeter. So you can actually use a direct ratio method like this. Okay, so you already have the 25 volts. If this one is found, you can now find out what is your V. So you probably would write a working similar to this. You will probably just say that at x equals to 0.4 centimeter, rather than saying potential V, it probably be better for me to say the potential difference is actually 0.4 divided by 1.2 times 75, giving me 25 volts. And then the equation is half mv squared q delta v. My mass of alpha particle is 4u, so it's half 4u v squared. And then q delta v, the charge of my alpha particle is 2e, so it's 2e times delta v. After that, you just sub in all the relevant values. You will get the answer as 4.91 times 10 power 4 meter per second. Okay, this one I don't need to write the 0 now. I already know it's 25. Okay, so that is for that particular part. There's one particular question from a long time ago, I think a few lessons before that I told you to skip, right? Let me just go through that question with you. It's a small part lah. I need to find out where it is. If you just look at page 27 actually. Page 27, June 17 P42. There was that last part C, that I mentioned that should be skipped at that time. Here, what you have is this. Let me just give you a brief idea of the question. You have two charged metal spheres A and B that are situated in a vacuum. The shortest distance between the surfaces of the sphere is 6 centimeters. A movable point P lies on the line joining the centers of the two spheres. A distance x from the surface of sphere A. The variation with distance x of the electric field strength at point P is as shown in the figure below. So this time is not potential versus distance, but electric field strength versus distance. Okay. Then after that, there's a lot of all these little questions here that you guys should have probably done. It's just part C that I want you to look at right now. In part C, they mentioned that use the figure, the graph, to state the value of x at which the rate of change of electric potential is maximum. Give a reason for the value that you have chosen. Now, this part here is where you need to be careful a bit. Last time I told you guys before, whenever you see the mention of whenever you see rate of change of something, rate already by right means per unit time, right? Okay. But in the context of your current question here, rate of change of electric potential isn't talking about change in potential over time. This is not the one that they're referring to. What they're referring to is the rate of change of what they refer to as rate of change of electric potential here is actually the change in potential with distance x. This is what they are actually referring to. So when you read this question, they ask you to state the value of x at which the rate of change of electric potential is maximum. It's asking you about this part, delta V, delta x being maximum. Okay. And delta V equals delta V or delta x, this one is actually equals to your electric field strength. Okay. So delta V over delta x is potential gradient. Is the gradient of your Vx graph, which in turn will be equals to your field strength. So they want you to find out where is your field strength, where is your rate of change of potential gradient, where they want you to find out where is the rate of change of electric potential maximum. In other words, where is your potential gradient maximum? Where is your gradient Vx maximum? That one can be inferred from your field strength value. So you look at your graph here, you look at the value of your field strength. The values of your field strength, you can consider this one, or you can also consider this one. Okay, but in terms of magnitude, which one is larger? You don't bother about the negative sign, you just look at the magnitude. This part here is where you have highest E magnitude. Highest E magnitude, therefore highest delta V, delta X. Okay, that's how you would do this question. You will write something like this. Electric field strength is your potential gradient. Your rate of change or electric potential is going to be maximum when your field strength is maximum. So it's at the x equals to 6 centimeters that your rate of change of electric potential is maximum. Okay, you look at the part where your field strength is maximum. That is where you are going to have maximum rate of change of electric potential. Okay, so that is for this particular question. All right.